So I'm going to start talking about the particles that come out of a radioactive nucleus decay. So the first one, and these first three are naturally occurring radioactive particles. The first one is a helium nucleus. It's written this way, 4/2, and it's described as an alpha particle. The second one is going to be a beta particle, and that is written this way. It's actually an electron moving at close to the speed of light, and this is called a beta. And the third one is just a real high energy form of electromagnetic radiation, which is another name for light, and it's called a gamma ray. So these are the three particles that are emitted during a radioactive decay of a nucleus. Now, I'm going to show you how the chemistry works on these. And I'll go back to an alpha particle. So I'll take, for example, the nuclear decay of uranium. And the uranium that I'm using is uranium-238. So that's the atomic mass. The atomic number of uranium is 92. And what it does is it gives off an alpha particle, helium, 2, 4, and it's very important to, when you're writing down nuclear reactions, that you put the atomic number and the atomic mass in the right places, because it becomes a real simple balancing act. Now, this is going to produce something. Well, it turns out it produces thorium. So this is transmutation. We're turning one element into another element because we have the protons changing. And what you do, it's really pretty simple. You sit there and you look at what the mass numbers are, and you just mathematically figure out what thorium is going to be. So, for example, in this case, it's 238 is going to equal 4 plus, and the answer is going to be 234. So it's the isotope of thorium that comes out of it is 234. All right? So 4 right here plus 234 equals 238 over here. And you do the same thing with the atomic number, which is the number of protons. So you look at this, well, 92 is going to equal 2 plus 90, and that indeed is the mass number for thorium. Not mass number, atomic number, number of protons of thorium. So during an alpha particle decay, what you find is the atomic number decreases by 2. I started off at 92, an alpha particle came off, I decreased the atomic number by 2, resulting in a new element, thorium. All right? Pretty simple, okay? Here's a beta reaction. Let's again take this thorium, and we'll start off at 234, thorium. Thorium's atomic number is 90. And this time I'm going to give off a beta particle, E. Have to write it that way. An electron has no mass, 0, has a charge of -1. And now for the easy part, okay, so what's going to happen? 90 is equal to a -1 plus, well, it would have to be 91, because 91 plus -1 is going to be 90. Element 91 turns out to be Pa, and there's no change in the mass number, atomic mass. All right? So again, what I'm doing is I'm just going straight across. 234 equals 0 plus 234. 90 equals a -1 plus 91. And like I said, nothing happens with gammas. Now there's two more particles that sometimes you can use for balancing, and these aren't considered natural radioactivity, but we mess around with them when we're talking about the chemistry, because sometimes they're useful. The first one is an electron that has a positive charge, and it is called a positron. And the next one that you're going to use sometimes is a neutron for neutron bombardment. A neutron in radioactive chemistry would have this symbol in, zero charge, a mass of 1, and so that's going to be a neutron. So those four, a beta, alpha, positron, and neutron, are the particles that you use to balance a nuclear reaction. All right? So here would be an example. This would be something, okay, let's just say I give you this. Here's aluminum, an isotope of aluminum, 28, 13. It's going to go to produce this. Silicon, 28, 14, that's a 14. So I'm trying to figure out what particle comes off of that. Well, I'll go to the top. 28 equals 28 plus, better be 0, okay? Then I go down here, 13 equals 14 plus, well, it's going to be a minus 1. So what is that? It's a that, E, and it's a beta. So, yeah, that's how you do it, okay? So a beta particle is going to come off of that, all right? Now there's one more part of radioactivity, and it's the measurement of the decay, and it's called half-life. And the way half-life is, it's a measure of how potent really that radioactive process is. Something with a very short half-life is going to be very radioactive, and it's going to be giving off particles like crazy. Something with a long half-life won't be giving them off quite as quickly. By definition, half-life is the amount of time it takes to lose half the mass. Okay? So that's basically what's going on. So here's an example of a problem, all right? Let's say I'm talking about scandium 42. It's an isotope. And I'm starting off with a 12-gram sample. So this is what I have, 12 grams of scandium 42. Now, at some point, that 12 grams has turned into 1.5 grams through radioactive decay. And that duration of time to get from 12 grams to 1.5 grams took 252 days. So the scandium 42, this isotope, sitting on my table for 252 days, ended up going from a mass of 12 grams to 1.5 grams. How many half-lives? So what I want to calculate is, what is the half-life? So I'm going to find the half-life. So there are some formulas you could do it, but at this point, I think just kind of think it through, all right? So I'm going to take this 12 grams that I started out with, and I'm going to decrease it by 1/2. So that's 1/2 half-life. You know, that's 1 half-life. I'm then going to decrease it again, take that 6, halve it, and go to 3 grams. Finally, I'm going to go to the 1.5 grams that I'm trying to get to. Well, in terms of number of half-lives, I have 1, 2, 3 half-lives. All right? It was 252 days. Divide that by 3, 8, 24, 12, 4. The half-life is 84 days. Okay? So every 84 days, there's going to be half the mass there was in the first place. Where'd the mass go? It went to all those little particles that came flying off that we talked about, alphas and betas and that. All right, try it.